Thank you very much for joining us today. Good morning, good evening, good afternoon, wherever you are. In the first part of the presentation, I would like to focus on accurate mass LC-MS and would like to explain how this type of technology can be useful for water contaminant analysis. Quick overview about my presentation. So first, a couple of thoughts about sample preparation and other front ends before we feed our sample into the accurate mass LC-MS system. Then I would like to cover a couple of details of the technology and performance criteria of the SCIEX TOFT family before I dig into application data, and I would like to highlight a few features, how to quantify, how to identify known or unknown compounds in water samples, and highlight a couple of very important software features there. So before we start, we would like to ask you a question to get some information about what topics are you interested in. Lauren?
So we have two polling questions for you. The first polling question is at the top left of your screen, and the second one is at the right. The first one is, do you use accurate mass LC-MS in your lab for water testing? Yes, you're using it. No, that you're not using it, but you want to incorporate the technology in the future. Or no, you're not using it and you don't have plans to incorporate the technology in the future. And the second question is, what workflows would you like to use accurate mass LC-MS or LC-MS for in your lab? For targeted quantitation, for unknown identification, or a combination of targeted quantitation and unknown identification, or none of these apply. So again, are you using accurate mass in your lab for water testing? And what workflows would you like to use accurate mass for in your lab? So the results, we can see that there's a mixture of people out there who are doing, who are currently using accurate mass, and then who are not using it but are looking to incorporate the technology. And it looks like the majority of people are interested in doing a combination of targeted quantitation and unknown identification on their accurate mass system. Andre, did you have any comments on this?
Yeah, very interesting results. I expected that the audience will be a mix of people having accurate mass instrumentation in their laboratory or thinking about it, hence dialing in. And also, it's very typical that people combine targeted and non-targeted workflow with model accurate mass instrumentations.
Great, and thanks to the audience for participating in the polls. So now we'll go back to Andre's presentation.
Okay, let's talk about a couple of details about LC-MS methodology if we want to apply an accurate mass instrument for targeted and non-targeted analysis in our laboratory. First up, obviously, is sample preparation, and we can kind of like follow two procedures. The most easiest and most powerful, and also the most cost-efficient one, is skipping sample preparation completely and injecting water samples directly. Sometimes some filtering might be necessary. This works very well with all kind of like clean waters if we consider drinking water, surface water, groundwater, maybe. This is the ideal sample preparation technology if we want to cover as many as possible compounds in a multi-component assay, or if we consider non-target analysis. Anytime when we introduce a more complex sample preparation step, there's a risk that we remove compounds during sample preparation, and then of course we cannot find them in any non-target or multi-target method. If we do use sample preparation, most laboratories, whether use liquid-liquid extraction or solid phase extraction. Solid phase extraction is very popular since it can be easily automated. A little bit about that in the second half of today's webcast. These are very important extraction procedures if you need to concentrate our samples, because we have to achieve very low detection limits, something like in the very low parts per trillion or maybe sub-parts per trillion, or if we have to deal with very dirty environmental matrices and wastewater and some soils. Would be two examples of that. If we do not clean up these samples, there's a very high risk that we lose signal because of ion suppression in the ion source. If we think about the LC separation, also here the simpler the better. We want to separate, spread our analytes evenly throughout the chromatogram. We want to efficiently move them away from our matrix components to minimize ion suppression. Very generic reverse phase conditions, whether on traditional C18 or polar modified C18 columns, work very well with generic gradients of water acetonitrile, water methanol with a volatile buffer. Over the last couple of years, small particle size columns or core shell columns like the two columns I mentioned in the example chromatogram down here, the Luna 2.5 micrometer or the Kinetics 2.6 micrometers are very popular choices. And the chromatogram you see here, that's an example chromatogram where we detected a number of pharmaceuticals and personal care products. And these are very good chromatographic conditions suitable for multi-component analysis. If we think now about the mass spectrometer as part of the analysis, electrospray is the most commonly used ion source. This ion source can cover the broadest range of compounds. Sometimes if we have to deal with low polarity analytes, APCI or APPI, chemicalization or photoionization might be necessary to also include these analytes. But electrospray typically can handle 90, maybe 95% of target analytes. If we operate a triple quadrupole instrument, what is currently the most common analyzer in many laboratories, multiple reaction monitoring is the typical operation mode for its high selectivity and sensitivity. And we typically combine that with scheduled MIM for best data quality and to cover many compounds in a single analysis. It's very common to monitor 2 or maybe more transitions per compound. The ratio of these ions then allows us to identify compounds. That's also embedded into many guidelines for environmental analysis. On top of that, if we have a QTREP, we can acquire full-scan MS spectra, and they can be searched against mass spectra libraries, and that helps also with compound identification. If we now compare that to an accurate mass instrument like the SCIEX triple TOFT, here we have the ability to acquire high-resolution and accurate mass MS and MS spectra, both of them in a single analysis through information-dependent acquisition. And the combination of MS and MS is very crucial because on one hand, this information allows us to quantify target analytes, and I put here MIM like quantitation, modern time-of-flight instruments. They can really quantify analytes with data quality and sensitivity levels like we know them from triple quadrupole instruments. And then in combination with MS spectra, this allows us to identify whether targets or unknown compounds with very high confidence, and I will give you some examples later how that can be done. If we quickly look into the performance criteria of the triple TOFT family, the 4600 and the 5600 instrument, it combines a couple of attributes which are all together making it a very powerful instrument for environmental analysis. The instrument offers very high sensitivity. The 5600 is slightly more sensitive than the 4600. It has a high resolution, all the way up to 25,000 or 35,000, depending if we talk about the 4600 or 5600. It can acquire MS spectra extremely fast, up to 50 or 100 MS spectra in a single second. For most environmental applications, we are probably fine with 20 or 10 hertz only, so we don't need the full acquisition speed of the instrument. Mass accuracy is typically in the 2 ppm range, much better than necessary for identification purpose. Very important that we typically see 3 to 4 orders of magnitude for quantitation. That is a new feature pretty much of time-of-flight instruments. That's where the largest improvement over the last couple of years was achieved. And most importantly, probably, that the instrument comes with very intuitive and powerful software features allowing you to do quantitative or qualitative analysis, since data files of an accurate mass instrument are very complex. temperatures are very important to process them. This is kind of like the schematic of the triple TOFT instrument. In the front end, there would be the ion source, and then ions are transmitted into the ion part of the instrument. You can see the golden quadrupole in the middle. That's the first quadrupole where we can filter molecular ions we want to handle in MS-MS. Then behind is the collision cell, and then ions are pulsed into the time-of-flight analyzer region. And then we can measure there, based on their time of flight, the accurate mass of molecular ions or fragment ions. And by design, the instrument combines the power of qualitative analysis with many features which are necessary for quantitative analysis, such as sensitivity and speed and linear dynamic range for quantitation. How do we quantify? How do we get our selectivity in accurate mass MS? Experiments. Here is an example shown where carbamazepine was spiked into a water sample. These were samples we analyzed for USGS, and we extracted very narrow windows around the expected molecular ion for our target analyte, and I was extracting that with different width to play around with selectivity. On the very top chromatogram, you can see a window of 1,000 parts per million, then 100 parts per million at the bottom, 10 parts per million. And you can see, since we measure our mass very accurate, the more narrow we make the window for data processing, the more of our background interferences we remove, and that is optimizing the signal-to-noise value. And typically, in the area of 10, 20 parts per million, that's typically where the best selectivity for such experiments can be achieved. And of course, this data processing can be done in software. You don't have to type in these numbers manually all the time. Here is a screenshot of our MasterView software, which we can use to quickly screen and identify a large list of target compounds like carbamazepine in water, for instance. On top, we have the chromatogram, and in the middle, there's like a little data processing table where you provide the compound name, and then also where you provide the molecular formula for your target analyte and retention time. And the software then uses the molecular formula to calculate the accurate mass information for each target analyte and will automatically extract that information from your chromatogram. And anytime a peak is present in your sample, the software will automatically evaluate the accurate mass MS information. It will look for the mass accuracy of the molecular ion and also for isotopic ratios. And at the same time, it will automatically take the MS-MS spectrum, also saved into the data file, and search that against our mass spectra library. And all these four criteria together result in very high confidence of identifying targeted compounds in water samples. If we think about quantitative analysis, here's an example. Carbamazepine was quantified over 3 orders of magnitude. Percent CV is typically in the below 5 to 10%. So it's a very, very comparable to triple quadrupole quantitative results. And this data I was showing, that was focusing on using accurate mass MS information to quantify. And of course, with a mass spectrometer, there are different ways to increase selectivity for quantitation to get the best signal-to-noise ratio. On triple quadrupole instruments, we would use the MS-MS capabilities, multiple reaction monitoring. On the triple TOFT instrument, we would use the mass accuracy and resolution of a time-of-flight MS experiment. But we can also combine these two, and we can operate the instrument in MS-MS mode together with the power of accurate mass, and we would call that MRMHR. And in this slide, there's a little comparison how the instrument is what results you get out of the instrument operated in time-of-flight MS mode, or in MHR mode. If we quantify carbamazepine in TOFT mode, extracting narrow windows of 10 millidalton around the expected molecular ion, we have a limit of quantitation somewhere around 10 parts per trillion, 10 nanogram per liter, signal to noise of 6, and good reproducibility. If we do the exact same analysis in MHR mode, combining mass accuracy with MS capability, you can see that our interference, our background is removed due to higher selectivity. Our signal to noise improves, and we can quantify at lower levels. So that's a quite important feature which allows us to further increase selectivity for quantitation to monitor target analytes at even lower levels. Just some data about findings of carbamazepine. A while ago, our team did some water sampling across the world when traveling, going to conferences, going on vacation, etc. And we sampled drinking water, river water, lake water across the world in different countries. And here are some findings about carbamazepine. In total, we had 70 water samples from all different countries. And if we look into the signal from carbamazepine, you can see it's widely distributed in many rivers and drinking waters throughout the world. Carbamazepine is one of the most widely used pharmaceuticals all over the world. And in many countries and geographies it can be found. And it's also well known that carbamazepine does not degrade during the drinking water treatment process. So in many countries, the levels we can see in drinking water are very, very similar to river water. And the highest finding we had was the drinking water collected in Berlin, in Germany. So, but how about the unknown analysis now? Accurate mass information can also be used to identify unexpected and unknown compounds in complex samples. And here the biggest challenge is not data acquisition. The biggest challenge here is more the data processing. It's when you look into a full scan accurate mass chromatogram, it really looks like a forest of peaks, and it's very complicated sometimes to identify which of these many peaks in the chromatogram is really an unexpected pollutant in an environmental sample, and not just a natural, normal component being present in that water sample or environmental sample. A very important trick is here basically to compare different samples. So that can be done in an easy way by having a contaminated, suspicious water sample. I picked an example here of a lake water sample coming from an urban area in Europe. And I compared that to a control water sample, which was a clean water sample coming from a stream more up in the nature, in the mountains, where I expected less influence from humans. The MasterView software can take these two water samples. It can go through the chromatograms, identifies all the chromatographic features, and then it compares these chromatographic features against each other to identify which signals are unique for our urban contaminated water sample because they're not present in our control sample. And here the software very easily identified one big peak which was present in the lake water sample but not present or present at very low level in our control river water sample. Once this peak is identified, everything kind of like becomes kind of like easy. The software automatically is going into the MS information to calculate the molecular formula. And it also takes the MS information, and that can be searched against large MS libraries, but also can be searched against the internet, against ChemSpider, to identify possible structures matching this molecular formula which was predicted for that water contaminant. So how does that work? If we look into the details of the formula finder, it does a couple of things to make sure that the list of molecular formulas calculated for an unknown compound is quite short. So it, of course, first uses the mass accuracy of a molecular ion. It also looks into the spacing and the ratio of different isotopic peaks to predict molecular formulas. The software also looks left and right of the molecular ion for the presence of different adducts. So for instance here, there was an M+ ammonium ion, M+ sodium ion also present. So that tells us that this ion here on the very top must be the M+ H ion, for instance, of our molecular formula. And then also the software takes all predicted molecular formula and chops it into theoretical pieces and double checks if these theoretical pieces are present in our MS-MS spectrum. And all these four features together, they typically result in a very short possible list of molecular formulas. So for instance, for this example in the water sample we studied here, there actually was only a single formula which could explain the MS and MS-MS ions. And then once we know the molecular formula, the software automatically evaluates the MS-MS information. We search the formula against the largest library of the world, the internet. ChemSpider is a great resource for any kind of like chemical structures which have been published in any way. And here we quickly could identify a DEET, a mosquito repellent, being the reason for our contamination in our urban lake water sample. And once a structure is suggested by the internet search, the software automatically also compares a chemical logic and the chemical structure with accurate mass MS-MS ions and gives us a score how well this structure can be explained with the MS-MS ion. And here the software can explain 100% of the fragment ions based on that structure. So that gives us also a very good confidence that we actually have the right compound. And then, of course, in the next step, we will need to get a standard, which we did, and then we confirm it by injecting a standard into the same technique and compare chromatographic retention time and also the accurate mass MS and MS-MS information. And once we also have a standard, then we can perform a quantitative analysis. And here's an example, a couple of environmental samples which have been collected on a canoeing trip in Algonquin Provincial Park in a couple of hours north of Toronto, where our office is. We took a couple of water samples throughout this canoeing trip, and you can see that the DEET concentration in the lake water goes up and down. It's very much connected to the tourist use of these lakes closer to the highway, where you have more people. You have higher DEET concentrations than you do have in the interior of the park, with the little exception of sampling number 5. That is a very, very small lake right after Long Portage, where people typically spray lots of mosquito repellent while carrying the canoe, and then afterwards jumping right into the lake to wash it off and feel more comfortable. So this is kind of just a little sampling story following a series of lakes where we monitored, quantified the amount of DEET in these water samples after identifying DEET as the unknown contaminant. So quick summary of that presentation. Accurate mass LC-MS very powerful for quantitative and qualitative analysis. We can easily quantify environmental pollutants at trace levels. Pharmaceuticals, personal care products, pesticides are just a couple of examples what type of compounds can be analyzed. Big interest right now in identifying unknown, unexpected environmental metabolites or degradation products of these compounds. Also, direct injection and a generic LC separation is the easiest way to bring these unexpected compounds into the mass spectrometer. And the triple TOFT data acquisition speed and software logic allows us to collect MS and MS information of every compound in all the samples, which is very important to identify unknown compounds. And then I just gave you a couple of examples how powerful and intuitive the MasterView software can be used, whether to identify targeted compounds in our samples based on MS and MS information with very high confidence, or to identify unexpected compounds by finding molecular formulas for these compounds and then searching them against mass spectral libraries and the internet to look for matching structures. With this, I'm at the end of that little presentation, and I would like to say thank you for listening. And if there are any questions, I would be happy to answer.